Welcome back to ECE 442-542. Homework number 3 is due on Monday. Homework number 4 is due the following Monday. And exam number 2 is in 2 weeks. That hopefully was not picked up on the recording, and I won't repeat that comment. But there are additional resources for homework number 3. You might want to look at the notes for complex poles. That might help you do some of the homework problems, and the region of convergence material is also under Unit 2 or under Unit 3. Homework number 4, I now have posted some discrete equivalent resources that you can now make use of, and hopefully we'll get through a fair amount of that today so that you have also today's material for discrete equivalence. And that's what we plan to do, go over discrete equivalence. First, I will scroll through so you can sit back and try to take in the concept of what we mean by discrete equivalent. And it doesn't mean one thing. It can mean many different things, and you have to be tuned in to what it is that you're trying to accomplish in order to perform a discrete equivalent. We'll start going through the details with one particular technique, which is called a zero-order hold equivalent, and we'll give several examples of that. Then we'll go to another type of finding discrete equivalence, which is roughly referred to as numerical integration techniques, and we'll have several of those. And then we'll do a pole zero matching approach to discrete equivalence, which means we're going to have about 5 different ways to find discrete equivalence once we get to exam number 2, which is in 2 weeks. Okay. Here's where you sit back and enjoy from 30,000 feet this overview. Discrete equivalents are a way of converting from a continuous time description of a filter, a controller, or a plant, and by that I'm now saying the filter I'm describing by H of S, the controller by C of S, and a plant by G of S. We want to be able to put those into a Ztransform description or into discrete time in the frequency domain. That's what we're trying to do with a discrete equivalent. We're trying to go from an S domain to a Z domain representation so that we'll end up with a H of Z, a C of Z, or a G of Z. That's the idea. Or you might say, what's behind? You can do this. You can do continuous to discrete or a discrete equivalent within MATLAB with one command, and it will produce the result that you want. You simply have to tell it as one of the arguments which approach you want to use. But this gives you a way to find the answer in the back of the book if you're now doing discrete equivalence on your homework. Maybe not on the exam. I'm not going to allow you to use MATLAB on the exam, but at least for the homework, you can check your work with C to D. Here's our generic block diagram of a continuous time system where we have our controller, we have our plant, and we could have feedback dynamics. Sometimes we simply have unity output feedback, and we sometimes suppress the negative unity output feedback in our description. So H of S would just be a 1. The transfer function for our feedback path would be 1. But our plant typically is something, a first order, a second order, some kind of G of S, and we typically have some kind of controller. I'm circling or highlighting those 2 parts of this continuous time block diagram because we may want to find a discrete equivalent for our controller, or we may want to find it for the plant. And there's different ways of finding those discrete equivalents. That's why we have 5 different ways that we're going to be talking about in this class. Do you see two different highlights, a blue and a yellow? That then is what I'm trying to say gives rise to two main situations or scenarios or reasons for wanting to find discrete equivalence. One reason is to convert a controller or a filter. That could just be maybe you want to implement a low-pass filter with a computer, and you now know how to design a low-pass filter, an analog low-pass filter. Maybe you have a transfer function. You want to find, how do I implement this with a difference equation? That's technique number one, or scenario number one. How do I obtain a C of Z from a C of S, where C of S is this transfer function description of a filter. It could be a low pass, it could be a band pass, it could be a high pass, but you want to now go into a discrete time, and once you have capital C of Z, you should be able to find a difference equation for that. And now you guys are expert programmers. That's what this symbol meant. You can now code that up into a difference equation, and if somebody now gives you a signal, a waveform, which is just a string of numbers, you can filter that string of numbers with your difference equation and generate the filtered waveform. That's scenario number one. How do you either get a filter or a controller into a Ztransform description? The other scenario is if you have a plant or a system and you want to find a discrete version of that, because you might want to analyze the system in a discrete setting, or you may want to design directly in the Z domain, and you need a transfer function G of Z in the discrete time case. You now need a G of Z, and we'll then have scenario number two, which is converting a plant, and that one we will usually use a zero order hold equivalent, which means that we're preceding our plant with a zero order hold. And we'll get into that now in pictures. Here's a simplified block diagram for scenario number one. And this is now a sampled version of the analog scenario, where now I'm simply illustrating one of the input-output configurations from the reference input to the output Y. I'm getting rid of some of the other inputs, the disturbance or the noise inputs. That's okay. But now what we're wanting to do is we're trying to now create a C of Z so that you could actually put a microcontroller or a computer in the feedback or in the system block diagram to actually control this system. What are you going to need? Well, you're going to have to sample the air signal, go from analog to digital. Now you'll have a string of numbers that you can input into or feed into your C of Z or your difference equation, and then that will just pop out a sequence of numbers, and you'll have to apply that to your plant. And in this case, you need to now convert that digital to an analog. If you tried to drive a motor with a sequence of numbers, you gave it 1.6, and then a little bit later you gave it 1.65, it's going to be just getting boom, boom, boom. It's not going to react very well. So you somehow have to convert that digital string or digital sequence of numbers into a continuous or an analog waveform, and that's the D to A. And we will simply apply a hold, which means you give me a number, I'm going to hold that value until the next sample period. You give me another number, I'm going to hold that until the next sample. So it's going to be flat, it's going to look like a stair step, but at least it's continuous time in nature. We want to be able to find what capital C of Z is if we started with a C of S. Maybe somebody came out of 441A or 541A. They have an analog controller that they've designed, and now they're in a senior project, and they go, you need to do this with a computer. I had my op-amp circuit all built. No, you have to replace it with a computer. Now you can implement that C of S with a C of Z. That's the idea. That's scenario number one. Scenario number two is the other piece, which is now we want to take a plant, G of S, into a G of Z, which now says that we actually, if there's any dynamics going on in that hold device or in the sampler, we need to incorporate that into our transformation from G of S to G of Z. We want to put all of those pieces together into our now available G of Z that we can now analyze with or design with. Meaning, we will now say G of Z is a discrete equivalent of G of S, just like C of Z was a discrete equivalent of C of S, but now they have different purposes, or they are trying to accomplish maybe different things. Here we will actually say, oh, since we are incorporating that digital to analog, or that hold, into our expression of G of Z, we're going to call this a zero-order hold equivalent for our discrete equivalent. Questions on that higher order or that high level? Here's now what we want to start with. Now what we want to do is extract that G of S and the preceding and the post operations of a hold, a D to A. So now coming into the input side is just a sequence of numbers. And it's in the frequency domain. Now we've Z-transformed those, but that could be little u of n. And now it's just this sequence of numbers that you're applying to your plant. Your zero-order hold will hold those in between each sample period, and that's going to drive your system. And then you will sample the output consistent with how you were sampling or measuring the input or injecting the input. We want to now incorporate all three of those pieces into our representation G of Z, which is a discrete equivalent of our original plant G of S. Now we can go up, or actually go down now, and start to derive what we are wanting to do relative to finding G of Z. And the first thing that we are going to do is look at the two different sides of G of S. G of S we're assuming we can find. That could be a mechanical system that you've now modeled. You found the differential equations, you've found its transfer function. Maybe it's an electrical circuit. Everybody loves electrical circuits based on the first exam. That just went cleanly on the last problem. Okay? So you should be able to find a G of S. Now that what we want to do now is focus on the input side, the zero-order hold, and the A to D side, see what kind of dynamics those present us with, and then put them all together to find how do we generate a zero-order hold equivalent of a generic plant G of S. Let's then find or examine the characteristics of the A to D, the analog to digital. That's on the output side. That's where we are actually sampling the output coming out of the plant. That's the output side. That's the A to D. And the other piece of that three-part combination is our digital to analog. That's the hold device. We will simply restrict our attention to a zero-order hold, meaning it's a zero order, it's just flat. A first order might be trying to do some kind of slope approximation between samples. Let's not do a first order hold. Let's just do a zero-order hold. And this is now on the input side. And we'll actually work our way from the simplest to the more involved. And the simplest one is the output side, the A to D behavior. Let's look at the characteristics of the A to D block. Again, as a reminder, that's at the output side. Conceptually, what we have is we have some output waveform. Let's say that's y of t. It's analog. But now we want to know, we really are trying to discretize our whole operation, and now we are going to be sampling this analog waveform at discrete points in time, t, 2t, 3t, 4t, etc. And if we wanted to think about that in terms of the analog to digital process, what does the digital, maybe I'll go ahead and call this t still. Now we want to know what is y of nt. That's now just a sequence of numbers. It's not this continuous waveform. It's simply, oh boy, now I have to try to make this somewhat accurate. So let me start here. So there would be y of 0. Then I would have y of 1, or y of t. I could emphasize that by saying that's the number at time t. Then we have the next number, which is y of 2t. We might just absorb the capital T or suppress the capital T. We might just say that's y of 2, and somebody has to have on the side the sampling period capital T if they need to go back. And then let's say here is our next value at y of 3, or y of 3t, and that just keeps going, just like this kept going. And we want to know what kind of dynamics. We're trying to capture this in the continuous time to discrete time setting. Are there any dynamics in this process of going from analog to digital? Now I am just sitting at the output and I'm taking pictures or measuring that waveform at particular instance of time. Is there any kind of dynamics associated with that measurement? What do I mean by dynamics? Is there any kind of memory? For example, an RC circuit has dynamics. A resistive circuit has no dynamics, does it? You inject an input, and the outputs or the other signals in your system are proportional, and they're instantaneously there at that measured spot. Here, we're saying, are there any dynamics between the analog to digital process at the output side? Is there any kind of memory? Is there any kind of holding behavior between what's happening in the analog signal and what you see in the discrete time signal? You're basically just taking a picture, right? At 0, at t, at 2t, at 3t. You're just clicking measurements. There's no dynamics. So this one's easy. We don't have to really worry about what we are going to implement or introduce other than the sampling process. There's no dynamic. We're not going to change the G of S in any way by this particular output side characteristic. That probably then hints that the input side might be a little different. Let's look at the zero order hold characteristics. At the input side, what we want to do, now we're going just the opposite. We're taking a sequence of numbers and trying to convert those into an analog waveform. We're going digital to analog. This is now the D to A. Or we would start with this sequence of numbers. Let's call it U of N. It may be the input of our system. Maybe it's here and it's there. These are supposed to be straight lines, straight vertical lines. And that's happening at T, 2T, 3T, etc. The zero order hold process is what I tried to describe before, which is if you give me a number, I'm going to hold that number with my hold device, with my zero order hold, and I'm going to apply that number for the entire sample period. So if this number is 2.7, I'm going to keep that 2.7 and apply it until I get to my next sample period T. Then at my next sample period, I'm actually going to maybe obtain another value, another number, and this is supposed to be consistent with my U of N, my sequence of numbers, and then I will hold that constant until the next sample period, 2T, and at that point somebody gives me a new number, and I take that number and I hold that for one sample period, and then at 3T somebody gives me another number and I hold that constant. Meaning I could have a sequence of numbers, and that might not work when it's applied to a physical system. If that was applied to a mass, that's not going to move that mass very effectively. You need to have a continuous application of a force. If you just said, okay, hit it with a number, well, then it wouldn't work that well. But it would somehow just, what, if you put it to a DC motor, if you just gave it 1, then you gave it 1.2, every so many sample periods, it's not going to be able to respond because it's got a gap there. You need to hold that through this zero order hold device. Let's now try to describe this behavior, this time domain behavior that's happening as a result of this zero order hold. Or what is the time response of the zero order hold? Yes, so the question was, how does this capital T compare to this capital T? We're assuming that those are the same. In this class, we're going to have one sample period, and it's going to be the same throughout. We're not going to be dealing with multi-rate sample periods or multi-rate sampling, which maybe somebody might do in their project. And we'll talk more maybe about projects before spring break so that you can work on projects over spring break if you're in the graduate piece of this class. If you're in the undergraduate piece, you can enjoy your spring break, huh? Yeah, I caught that. All right, so the time response behavior is, first let's apply a unit pulse. And unit says the pulse is going to have a magnitude of 1. And that's what we're going to apply to our zero order hold. What's the output of a zero order hold if we apply a 1, a number 1 to it? So now the output of the zero order hold as a function of time, let's say this is now the unit pulse response of our zero order hold, just like we might have a impulse response. Now we have a pulse response, a unit pulse response of our zero order hold, and that we will call G sub ZOH of t. What does that look like as a waveform or as a function of time? If at time 0 we apply a unit value, that's our unit pulse. So I'm now going to apply to this a value of 1, and what's the output of my zero-order hold look like? Looks like a rectangle, doesn't it? And how tall is that rectangle? Its unit. How wide is that rectangle? Can you tell that's a sample period, capital T? Please say yes. That took a lot of effort. That sample period T, so now you know what the sample period is, right? It's just T. So we hold that 1 for 1 sample period. Our rectangle has a height of 1 and a width of capital T. That's our unit pulse response of this zero-order hold. Now, what I want to do is I actually want to try to express, why do I keep, I want to express this in terms of fundamental waveforms. What's a fundamental waveform? An impulse, a unit step, a unit ramp. I want to now try to describe this rectangle in terms of fundamental waveforms, because I want to actually take this into the frequency domain. I want to try to find a capital G sub ZOH of S. That's what I'm after, so that I can now combine it with my G of S, which is my plant. My analog to digital at the output doesn't have any dynamics, so I don't have to worry about that, but this one does. In terms of fundamental waveforms, what if this was an analog and I said, oh, that would just be the unit step and it would just go on and on and on, right? In this case, it doesn't just go on and on, but we can deal with that. We can at least start with a unit step as far as what G of T looks like. And then we'll have to worry what we do once we get one sample period into the future, or at time step, or at time value capital T. But for starters, is it clear that the first piece of this way of describing G sub ZOH of T in terms of fundamental waveforms is just to say, let's turn something on, and that something that we're turning on is equivalent to a unit step, U of T. That's clear? Now what? We want it to be a rectangle. We don't want it to be infinitely wide, do we? We just want this rectangle to be as wide as one sample period. Can we somehow make that happen in terms of fundamental waveforms? I'm waiting for you to process or to provide me with an answer. That we've now turned on. We've turned this on. It's now a unit step. Can't we just take it away? At time step T, you're saying subtract it, right? What happens now if we say, oh, U of, and now what's my argument inside the U, the unit step? Pardon? I can't hear. I can only step, okay? Yes, T minus T. Did you understand that one of those was lowercase and one was capitalized? We had U of T, but we started it at capital T and in time, and we want to take that away from what we started with, which was U of little t. So now we're trying to subtract a unit step. That's a value of 1, but we want that one to start at time step or at time location capital T. And the argument of U of T minus capital T becomes 0 right at capital T. So that one kicks on at little t minus capital T, and we're taking it away. Question? So now, is there a reason why we're doing this with subtraction instead of multiplication? Good question. Why would we want to do that? Because addition and subtraction, linear operations are easier than multiplying waveforms. So this makes it easier for the analysis or the description. Because we don't want to, multiplication in the time domain would correspond to convolution in the frequency domain, and we get a little nervous when we start talking about convolution. That's the whole point of going into the frequency domain. We're trying to make it easier. I apologize for those that are listening. They don't see the animation that's happening. But I guess it's not going over very well. So this is now what? Here is a unit step that's delayed by one sample period, capital T. And this is really what we're after. This is now the unit pulse response of our zero order hold. As I said, we want to multiply in the frequency domain. We don't want to be convolving in the time domain. That's kind of messy. So let's now find the frequency domain version, or let's Laplace transform this little g sub ZOH that we've now represented in terms of fundamental waveforms that we can find Laplace transforms for quite easily. That's why we're trying to describe it in terms of fundamental waveforms. Let's go into the frequency domain. And we're still analog, so this is now using the Laplace transform in the frequency domain. What is capital G sub ZOH of S? What's the Laplace transform of a unit step? Or what is U of t? As a waveform, that's just a constant waveform, isn't it? And what's the Laplace transform of a constant with magnitude 1? 1 over s, right? That's a signal that's different from an operator. If that was if this 1 over s was corresponding to an operation in the time domain, what would the operation be? Position I don't know why I thought it went into the operating room, but what's the operation in the time domain that corresponds to 1 over s in the frequency domain? What integration? If you multiplied by s, that's like differentiating in the time domain. So 1 over s as an operator, if you said, oh, this is actually an operation, then that's an integral in the time domain. But now it's representing a waveform in the frequency domain, so that waveform is just 1. What's the Laplace transform of a delayed unit step? And if you were looking for points on the exam, you would say, oh, it's a unit step, right? You'd at least get part of the answer. It's a unit step. But what do you have to do with it if it's delayed? It's an exponential, isn't it? It's this e to the minus, and it's now delayed by a particular amount, our sample period. It's e to the minus capital Ts. That's now the Laplace transform of this delayed unit step, and we can now subtract those two Laplace transforms. That's why we like to model this in terms of combining with addition or subtraction. It makes it easier. to perform the Laplace transform. Or we could now describe this. We can combine this. We have a common factor of 1 over s. We can say, oh, that's 1 minus e to the minus ts times 1 over s. Or I might just put that on top and say this is 1 minus e to the minus ts over s. And that's now my frequency domain description of a zero-order hold. And that's going to allow me now to think of this combination of 3 blocks here is the transfer function of my zero-order hold. That's the A to D. I'm sorry, that's the D to A. That's going from digital to analog. Here is my plant, G of S, and here is the A to D. We've now figured out what the dynamics of G sub ZOH look like. Let's call that combination capital Y sub 1 of S, and that's now 1 minus e to the minus TS over S times G of S. We're keeping G generic because we don't know whether that's going to be a first order system, a second order. We want to just develop this expression in terms of a generic G of S. But it will be some linear system that we can describe by a transfer function. This is now really the Laplace transform of the unit pulse response of our system. What we want to do is now use that to try to find a capital G of Z. So we now need to somehow take this into a discrete time setting. So let's look at what we have. We have Y sub 1 of S, which is now this 1 minus e to the minus TS, and that S is always sitting there. Let's just put that underneath the G of S. This is now G of S over S. Or we could, if we wanted to, it may be cleaner sometimes to distribute that common G of S over S between the two terms. Or I could now call Y sub 1 of S this combination of G of S over S minus e to the minus TS. That's just a unit delay in the frequency domain times G of S over S. What I want to do now is to get this into a Z domain, I need to somehow come up with a sequence of numbers and then Z-transform that sequence of numbers. But this is a signal, little y sub 1 of t, in the frequency domain. If I inverse Laplace transformed this and then sampled that resulting waveform, I would have a sequence of numbers I could Z-transform. Let me see if I can make that notation. I'm now going to have a capital G of Z. I'm going to say, oh, that's the Z transform. That's what that script Z is supposed to be representing. And now I'm going to symbolically say, oh, these dashed vertical lines are symbolizing the sampling process. And that's going to sample the inverse Laplace transform of y sub 1 of capital Y sub 1 of S, which would give me little y sub 1 of t. And I'm going to sample that little y sub 1 of t. That sampled sequence I can Z-transform. This vertical dashed line is the sampling process. this is just little y sub 1 of t, which is my continuous time signal. That's the unit pulse response of my system. And this piece, that curly bracket, is now underlining or identifying what's coming out from the sampling process. This is now a discrete time signal. Now that's going to get a little tiresome to keep doing this, right? And we want to be efficient. So I'm simply going to define g of z to mean what I've just diagrammed out. When I say I want to find g of z, then what I'm going to do is I'm going to say, oh, g of z, whoops, I'm going to say that g of z I'll define to be the Z-transform of y sub 1 of s. And when I say that, what I'm really doing is what was just illustrated above that. I'm inverse Laplace transforming capital Y sub 1 of s to obtain little y sub 1 of t. I'm sampling it, and then I'm Z-transforming that sampled signal. That's what I'm defining to be this Z-transform operation. Now, what was y sub 1 of z? In our case, that was two parts. It was the Z-transform. Now, if I use that same notation, I simply need to Z-transform g of s over s, and I'm going to subtract from that e to the minus ts g of s over s, or a delayed version of that same g of s over s. But what is that e to the minus ts? What does that really represent? It's the Laplace transform of something, and what is it the Laplace transform of? If you saw a Laplace transform expression and it contained this factor e to the minus ts, and you had to inverse Laplace transform that, what would you do in the time domain? You would just delay that result by how much? T units of time. So e to the minus ts is really just representative of a delay of one sample period, capital T. Note that e to the minus ts is the Laplace transform of a delay of t seconds. And if I said, give me a Z-transform of a unit delay, what would you hand me? You went to the store and went to the counter and said, I need the Z-transform of a unit delay. What will they give you? Besides a swift kick or a slap in the face, right? What would we give you? If you went to the stockroom and asked for the Z-transform of a unit delay, they should hand you your CAT card back. It hasn't been that long, has it? What's the Z-transform of a t-second delay? How did we represent that? Isn't that the frequency domain representation of a unit delay? It's just z to the minus 1, which now allows us to, if you had that e to the minus ts in 340 or 320, you would start getting nervous, wouldn't you? You'd be going, oh my goodness, what's going on? Really? I have to do that? But in this class, that's convenient. It now just becomes z to the minus 1. Meaning, we can now re-express this two-term expression of the g of s over s, subtracting away this unit delay. We can now rewrite that, knowing that the unit delay is z to the minus 1 in the frequency domain for g of z. We can now say, oh, I now can say g of z is the z transform of g of s over s minus z inverse the z transform of g of s over s. Or, now if somebody says, oh, I need the zero order hold equivalent of g of s, well, now it just becomes 1 minus z to the minus 1 z transform of g of s over s. So you take that g of s, put another s in the denominator, another pole at the origin, find the z transform of that, and then multiply it or pre-multiply it by 1 minus z to the minus 1. But 1 minus z to the minus 1 is simply put that z to the minus 1 as 1 over z and find a common denominator. That's z minus 1 over z. Piece of cake. All right, so let's now summarize what we've just derived. If you now need to find on the exam the zero order hold equivalent of a transfer function, of a g of s, or you might be asked not the zero order hold equivalent, but somebody might say, give me the pulse response transfer function. It's the same thing. Okay? So this is what happens if you hit your system with a pulse. It's the pulse response, but it's in the frequency domain. This is the pulse response transfer function. That now is simply g of z equaling 1 minus z to the minus 1 z transform. And remember how we're defining this z transform curly braces thing. We would take, if we needed to, if we had to break it down, but we'll just be able to use the tables and find these pairs. But if we had to physically think through what's going on, we would find g of s over s, take it into the time domain, sample it, and then z transform those samples. That's what we're doing by this z transform script z curly braces what's inside. Let's look at some examples so that you can maybe make a connection between what you already know about g of s's, certain plants, and what their zero order hold equivalents might look like. Examples of zero order hold equivalents. Meaning, you don't have to rederive what we just derived. You just have to understand it, and if I say zero order hold equivalent, boom, you apply that expression and you do what we're doing now, which is go through some examples. Let's look at the first example, and let's not start off by sprinting. Let's just start crawling. Okay? So let's find a system, a g of s, that's like crawling. I would get down, but that's not going to come through on the audio, so I'll spare you the crawling across the floor. Suppose that our system is just 5. You give me an input, and I scale it by 5. That's as simple as it gets, isn't it? It's just a constant. Or, really, we should think of it as a system operation. As an operation, it's simply a gain. And this time, it's a gain that's bigger than 1. It could be a gain that's less than 1. It's just a gain. But this is now just a gain. Let's see what happens when we now want to find the zero order hold equivalent, which in block diagram terms is compacting or putting all three of these pieces together. We now want to find what is the g of z associated with a plant preceded by a hold. And our hold is particular. It's a zero order hold. So this is now the zero order hold equivalent of a system that's actually quite trivial. It's a game. Or we're saying, what is the pulse response transfer function when our system, our original system, our g of s, is a game? If you wanted to get some partial credit on the exam, what would you immediately write down if I said, give me the zero order hold equivalent of g of s? You would just look at your note, your crib sheet, oh, I forgot to put that on. Don't forget to put it on. Okay, it's now 1 minus z to the minus 1 z transform of g of s over s. Now you have a start. Well, you can just keep going. You can hope for inspiration as you're writing, right? So now you go, well, he gave me what g of s was. That's 5. So let me just put that in here. 5 over s. Okay, I'm looking for inspiration. But I can factor that 5 out of the z transform. That's just a constant. That's just a scaling. So I now have 5. 1 minus z to the minus 1, z transform of 1 over s. And what is that 1 over s in terms of a signal or a waveform? If we now did what we said we were doing inside this notation, we're saying, oh, take that into the time domain, analog, continuous time, sample it, and then z transform the samples. If you inverse Laplace transformed 1 over s, what are you going to end up with? That's just going to give you a 1, isn't it? If you inverse Laplace transformed. Now you want to sample it. So this is now what we're doing. And we have 5 times 1 minus, let me just see, let me write it in terms of z's instead of z to the minus 1s. I now have the z transform of 1 over s. And on the exam, you hope that you remember your z transform table, and you go, do I have anything that looks like a unit step sequence? In this case, it's a unit step sequence, right? And I don't have it labeled, but it's there, right? It's row 6 in this table. Yes? So now we go back, wherever back is, and we say, oh, from row number 6, and you wouldn't have to put this on the exam, but I'm doing it so if you come back to this notes and you go, where did that come from? Well, this is row 6 in the Z transform table. I need to have a wider piece of paper, so maybe I shouldn't have done curly braces. I'm not multiplying by that. That's just a comment. So if this was a cartoon, it would be a bubble floating above their heads, and it would be their wording, right? It's almost time. I apologize. So what do we have? We now, from row number 6, we have 1 minus 1 over z, but if I put that over a common denominator, I end up with z minus 1 over z. And what did we see that the z transform of 1 over s was? Wasn't that z over z minus 1? That cancels that, that cancels that, and what are we left with? This is supposed to be the pulse response of a gain for our transfer function, and that becomes 5. That kind of makes sense. If we just have a gain for our plant in the analog case, good. We put a zero order hold in front of it, and it's still going to look like a gain in the discrete time setting. Meaning G of Z, our zero order hold equivalent of a gain, is just going to be a gain, and we haven't changed the value of that gain in any way. So this seems to make sense. Let's go up a notch. Let's now look at a zero order hold equivalent, or suppose zero order hold precedes a pure mass system. Now what I have is I have a zero order hold, and I have a system which I've called G of S before, but this system is not just a gain 5, it has the dynamics of a pure mass. And I want to know what is this. What is capital G of Z, the zero order hold equivalent of that. Now, for all of you that were in 441A or 541A, you should just be able to tell me what G of S is. You maybe didn't take 441A or 541A, or maybe you've forgotten what that might be. Shame on you. Don't be doing that. You'll confuse me. So let's look at a free body diagram of a system. Now we're trying to simply remind ourselves of what this G of S corresponds to as a transfer function. Now this block is a mass. Let me just call it M, and let's say that I've drawn a line in the sand, and that's the position of that mass, and now I'm going to apply a force to that mass. I'm going to call the force U of T. This is my force input. No springs, no dash pots, just a mass. I now have a mass, and I want to know what is G of S. What does physics tell us? Newton. What's he tell us? Force is equal to mass times acceleration, right? So that gives us some dynamics. We now know that U of T, the force, is mass times acceleration, and in terms of our position, the acceleration is just the second derivative of that position. F is equal to ma. We know that. That's all we're saying. F U of T is equal to mass times acceleration. And I want the transfer function between my input, which is the force, which is U, and the output, which is x, the position. Or I can now rewrite this and say, oh, my acceleration, or the second derivative of x, is 1 over m times U of T. Oh, I don't want to work with 1 over m, so let me just call that alpha U of T. And U of T is not the unit step. Is that clear? This is now a force. That's just a force that I'm applying. It's the generic input, and I'm calling this alpha. That's a constant that's equal to 1 over m. There's my time domain dynamics of a pure mass. I can give you the acceleration or I can tell you the acceleration if you tell me the mass, which you're telling me alpha, and the force that you're applying. What's the transfer function of that? Because that's really what we're after. We're trying to find capital G of S. You now have a second order differential equation. We want to go into the frequency domain, and we want a transfer function. What do we do when we're finding transfer functions? Do we have to worry about initial conditions? Initial conditions? If we're looking for a transfer function, no, we can set those equal to 0. Those are equal to 0, which now means we don't have to be subtracting these x of zeros and x prime of zeros multiplied by s, etc., from the Laplace transform of this time domain differential equation. What happens when we Laplace transform two derivatives? What's that equivalent to in the frequency domain? What's one derivative in the frequency domain consistent with? Multiplication by s. Now we have 2. So we multiply by s again. It's s squared. Or we now can say that we have s squared, capital X of s, equaling alpha times the Laplace transform of our force, which is just capital U of s. Are we okay with that? And we want the transfer function, which is now the ratio of polynomials in S between the input, which in this case is U of S, and the output, which is our position, capital X of S. So let's push everything to the other side. We now have alpha over S squared times U of S. And this, in brackets, is our capital G of S. Now it's not just alpha. In the previous example, it was just alpha and it was 5. Now we have some dynamic behavior. We have alpha over S squared. We basically have a double integrator with a gain, alpha. Let's find the zero order hold equivalent of two integrators, is really what we're doing. Let's find the zero order hold equivalent of G of S when G of S is now equal to alpha over S squared. And this is just a particular discrete equivalent. This is the zero order hold equivalent. But once I say zero order hold equivalent of G of S, what do you immediately write down? G of Z. And I think I actually heard it, didn't I? It's 1 minus z to the minus 1 Z transform of G of S over S. Or that's now 1 minus z to the minus 1. Sometimes it's just easier if you're a few steps away to just keep writing that as 1 minus z to the minus 1. But now we need to Z transform G of S over S, or alpha over S squared times S, or S cubed. Does anybody remember what would happen if we inverse Laplace transformed 1 over S cubed? What if we inverse Laplace transform 1 over S? 1. Give me a 1. What if we inverse Laplace transform 1 over S squared? Give me a T. What if I say inverse Laplace transform 1 over S cubed? T squared with a factor. So we have to be dividing out because but this becomes T squared over, you didn't hear when I said give me a T, you said T over 1 factorial. Then I said 1 over S cubed and you said, oh yes, T squared over 2 factorial. All right, now what are we doing? We won't do it yet. We'll probably do it the next time, but this would now, we would want to sample this analog waveform. We now have 1/2 times t squared. But what is t? When we sample, we're replacing little t with little n capital T. So we now have little n capital T, that whole thing squared. So now we want to Z-transform n squared. T squared is just a number. We can factor that out. Is that clear? So now we're Z-transforming n squared. So now it's this infinite sum of n squared z to the minus n. We'll derive that maybe next time. But now let's just go to the table. Because it's almost dinner time. We're going to sit down at the, this table. That's right. This table. What do we want? Oh, look at that. They're using little k's instead of little n's. I don't have that one labeled either, but do you see what row it is? Can we inductively figure that one out? It's row 8 of the table. So now we have n t squared. Wow, that gets a little bit interesting, doesn't it? But that's what our Z-transform is when we Z-transform that. So let's go back and fill in that piece of information. We now have g of z is 1 minus z to the minus 1. And we want to get that alpha and the 2 out of the way. Those are just scalars. Let's factor those out. And from row number 8, if you remember, that was t squared z, z plus 1 over z minus 1 cubed. That was row number 8 of k, the quantity kt squared, which we've been using instead of little k, n. But that was the quantity n capital T squared. Let's clean that up a little bit. We now have, this is z minus 1 over z, alpha over 2, t squared z, z plus 1 over z minus 1 cubed. Can we cancel? We can cancel a few things. We can cancel that z with that z. We can cancel one of those z minus 1 cubed factors in the denominator and get it at least down to z minus 1 squared, so that we now have for our zero order hold equivalent of a pure mass, it now becomes g of z is equal to alpha t squared over 2 times z plus 1 over z minus 1 squared. What was alpha? 1 over m. So if we just pick an m, give me an n. M, Michigan, 1. That's a good m. What if I give you a t? So now I'm calling out. Give me an m, 1. Give me a t, 1. Oh, great. So now we have a system, right, without all these unknowns. So let's make this easy, okay? We went to the table to have a fun time, right? So now let m equal 1. That's 1 kilogram, which in terms of our notation, alpha was 1 over m, so we can invert 1 pretty easy. And you were playing along nicely and said, let's let t equal 1. That's pretty slow. That's sampling at what? 1 time every second. That's a 1 hertz sample period. That's pretty slow. But now we have g of z for our pure mass is 1/2 z plus 1 over z minus 1 squared. And I think you're just dying to see that in the z-plane. Are you not? You just want to see poles and zeros. Because you're used to seeing, what's a double integrator in the s-plane? 1 over s squared. What would that look like? 2 poles at the origin. Now what do we have? Here in the z-plane, for a pure mass, where do we... Here's 1, here's -1, here's j, here's minus j. Can you tell me where I have poles and zeros for this pure mass with a mass of 1 and a sampling period of 1? The 1/2 is just a scaling. That doesn't impact our poles and zeros. Where do we have poles? 2 poles right on top of each other, right at 1. And where's our 0? We're going to find that that's infinitely fast. That's at -1. If we went around the unit circle, that's where we find our frequency response. That's as fast as we get in the z-plane. Is at, so now infinity is finite, isn't it? All right. So, but now you can compare this. And what do we know? We know z is equal to e to the st. Our double integrator had poles at 0 at the origin. We plug in s equals 0. Where are our poles here? E to the 0. 1. So now we have 2 poles at 1. That's consistent with what we would have expected. Now we have a a pure mass. We have 2 poles right at 1. Where's that relative to the stability boundary? Where's our stability boundary in the z-plane? The unit circle, right? It's right on the boundary, just like our double integrator. It's right on the stability boundary in the s-plane. All right. Well, that was sort of a big step. We went from crawling again to maybe jogging with this pure mass. Let's take it back a step. Let's just look at a pure integrator. What does that look like if we do the 0 order hold equivalent of an integrator? What's an integrator look like in terms of a system in the frequency domain? And let me say it has a gain of k. What's an integrator in the frequency domain? It's an operation k over s, isn't it? So this is now k over s. What was our pure mass? Trying to get dizzy. It was alpha over s squared. So that was 2 poles at the origin. Now we just want 1. We just want a pure integrator. What's the 0 order hold equivalent of this integrator? 0 order hold equivalent of an integrator. Boom, what do you plug in? What do you write down? What you have memorized after today's class. Oh, that's just capital G of z, which is 1 minus z to the minus 1, Ztransform of G of s over s. Well, that's just k over s squared. And now what do? We go back to the table, don't we? We just find, do we have a transform associated with k over s squared? We found one for alpha over s cubed, or 1 over s cubed. Now we have 1 minus z to the minus 1. This one will be kt z. Feel like that's a radio station somewhere. Anyway, usually has 4 letters, doesn't it? Oh well. It's just KTZ. Listen to KTZ. Never mind. You didn't know that was, never. Times z minus 1 squared. Or this now becomes z minus 1 over z times KTZ over z minus 1. We have some cancellations, don't we? So that we now have, whoops, how's that? Oh boy, you're really going to be nervous now. How about if I do that? Is that better? Peter would have caught that. Right? Are we okay? Now, oh, I need to cancel some more. Now, what's my zero order hold equivalent of a pure integrator? G of Z is now a gain K. It's the sample period, capital T, all over Z minus 1. And what's that look like in terms? So this is now the zero order hold of a pure integrator. Block, or I'm sorry, Z-plane pole zero diagram. What do you see? And don't say a hypotenuse. You have one pole at 1, correct? And is that consistent with a pure integrator in the what you're used to thinking in the S domain? Just a pole at the origin. Now the origin corresponds to Z equal 1 in the Z plane. So you now know how to zero order hold equivalent of a gain, of an integrator, and of a double integrator, and we'll move beyond that next time.